So we're going to start off our course talking about systems of linear equations, um, which is going to be kind of what's going to be going on in the background of pretty much everything we do in this class. Um, Today we're going to introduce a number of things that are going to recur really through the entire course. And systems of linear equations is kind of the basis of everything else we're doing here. So first off, what does it mean linear system? The system of linear equations, or a linear system, refers to multiple equations involving multiple variables. So in this case, we have a couple of equations. And the variables here are x sub 1, x sub 2, and x sub 3. In other courses, like Algebra 1 or Algebra 2, if you've seen these before, you've probably just seen x, y, z, which is fine. 2x minus y plus 1.5z equals 8 or whatever. Um, However, in this class, we are going to be using these subscripts because there may be more than three variables. There may be lots of variables. We just don't know, right? In fact, we're going to talk about generalizing. What if there are n variables? Well, so we are going to be using that subscript. It's just something to get used to. The word linear means everything is raised to the first power. Doesn't necessarily mean a line. For example, if I were to graph these in 3 dimensions, it'd actually be a plane. The word linear just means everything is raised to the first power. So there's no x1 squared or anything like that. And then the coefficients are the numbers multiplying the variables. And I'm sure you guys have, I'm not going to say sure, but I'm pretty sure you guys have seen these in previous courses. I just want to make sure we're all using uh, the same terminology. And then in general, a linear equation would look like this. So every linear equation, we have variables x1, x2 up through xn. Each variable has its own coefficient. So the coefficient for x1 is a1, coefficient for x2 is a2, and so on. Also, please notice that there's a number on the right side there, that b. That's just some constant that is not attached to a variable. So in our equation that we're just looking at, when we're talking about a solution means values of the variables that satisfy both equations. So a number we could plug in for x1, for x2, and for x3 that make both equations true statements. So in this example, one solution would be 5, 6.5, 3. What that means is if I were to replace the x sub 1 with a 5, so like in the first equation, 2 times 5 minus x sub 2, which is 6.5, plus 1.5 times x3, which is 3. We want to see if the result here is 8. Well, let's see, this would be 10 minus 6.5 plus 4.5, and yeah, that is equal to 8. So we plug it in and it does satisfy the equation. So it is a solution for the first equation. Of course, being a solution to the system means it has to make both of them true. So if I plug those numbers into the second equation as well, we get 5. There is no place for x sub 2, so I don't need that. Minus 4 times 3. And 5 minus 12 is equal to -7. So it also satisfies that second equation as well. So a solution means it makes both equations true. Um, in some cases, in some systems, there's one solution. In this case, there actually happen to be many solutions. So this is just one of many correct solutions. And so if there's more than one correct solution, we call that a solution set, right? And our goal, of course, is going to be to describe them all, and we'll get to that. Okay, two systems are equivalent. A big part of what we're going to be doing here is going to be involving taking one system and finding an equivalent system. But equivalent means we're changing the system, but we're not changing the answers. And that's the important part. We're going to talk about different ways of changing the system into an equivalent one. But the goal is still find the solution. Well, if we change it to an equivalent system, we end up still ending up getting the same answer. So we don't change the answers. Let's look at a couple of situations here. When solving a linear system of two variables with two equations, the solution is going to be the point where the graphs of the lines intersect. So, for example, if we're solving this system and we find a solution, well, please notice that there are only two variables. These are actually lines, right? In this case, it's a linear system, literally because they are lines. And so if I were to graph these two lines, it would look like this. Well, notice that the two lines cross at the point 3 comma 2. And so in this case, we end up getting a solution where x sub 1 is 3 and x sub 2 is 2. And if we were to plug both of those into the equations, they would satisfy the equation. Excuse me, they would satisfy the system. And so as a result, we end up getting one solution to this system of equations. Another situation is, what if we graph the two lines and they're parallel? Well, if our solution is where the lines cross, parallel means they never cross. So if we end up with two solutions, well, then we say that I'm sorry, if we end up with two parallel lines, we say there is no solution. And another way of stating that, and we're going to talk about this a little bit more as we go along, another way of stating that is that the system is inconsistent. So that's a word we're going to use a lot. Inconsistent means there is no solution. Third possibility is, what if you graph the two lines and they actually end up being the same line? The two lines coincide; they overlap each other. In this case, there are infinitely many solutions. Now, no solution we said is inconsistent. The word consistent means that there is at least one solution. So in this case, we had one solution. We could describe the system as consistent because there was one solution. If we had many solutions, we actually would also call that consistent. So the word consistent means there's at least one solution, maybe more, but at least one. The word inconsistent means there is no solution. Okay, now, in order to solve systems of equations, and by the way, you've seen these problems back in Algebra 1, Algebra 2. You've solved systems, and I'm sure you've learned different methods. Um, but certainly when you go beyond two variables, things become difficult. And so we're going to need a tool that's going to help us to solve equations where, what if it's not two equations with two variables? What if it's five equations with seven variables? What if it's three equations with four variables? It's lots of different situations. To come up with a more of a rigorous way of solving those problems, we're going to use matrices. So a matrix is a rectangular array that can help us to streamline the solving of a system of equations. So here's an example. This is a matrix. Um, as far as the size of this matrix, we're going to call this a 2 by 3 matrix because there are two rows and there are three columns. So just remember that the size of a matrix is the number of rows by the number of columns, so 2 by 3. In this book, we use these square brackets as we do in this picture. I've seen other books where there are curved brackets. That is perfectly acceptable. I don't mind if you do that. What I do mind, though, do not do straight lines like an absolute value. That actually has a different meaning that we'll get to later in the course. So don't use the straight lines. Also, don't use the curly brackets. That means something different. That's usually used to denote a set. But again, I'm going to use the square brackets. Your book uses square brackets. If you feel like you want to use curved bracket, like parentheses, because you've used that in previous courses, that's also perfectly acceptable. Okay, now the question becomes, how do we relate the two things? How do we connect the system of equations with the matrix? Well, by changing a system of equation into a matrix called an augmented matrix, we can make it easier to work with. So here's the system of equations, three variables, three equations. We're going to create this augmented matrix. Now, one thing that I'm going to do differently, and your book does not do, I'm going to draw a little line here. Now, where are all these numbers coming from? Notice at the top row, the 1, negative 4, 3, those are the coefficients for x1, x2, and x3. So we're taking the coefficients for the three variables and putting them in the top row of the matrix. And then the stuff on the right side is that 5. Notice that that line, that vertical line that I drew, is sort of like where the equal sign would go. So the 5, negative 3, 6, those are the numbers on the right side of the equal sign. So each row, I'm writing the coefficients for x1, x2, x3. Notice on the bottom row, there is no x2. So for that coefficient, I'm putting a 0. Also, it's worth noticing, and this will become useful to notice later on. Notice that this first column, all of those represent the x1 coefficients. The second column represent the x2s. The third column represents those x3s. Um, so it's just worth remembering that. Um, Also, please note, and this is really important, you don't put any variables in a matrix. A matrix is made up just of numbers. So this is what we call an augmented matrix. The word augmented, by the way, means that the matrix is broken up into pieces. Because we've got that line drawn through the middle there, we've basically considered the left side of the matrix and the right side of the matrix. We call that an augmented matrix. If we wanted to consider just the coefficients and ignore the stuff on the right side of the equal sign, we call that the coefficient matrix. Okay. Now, the reason that I really like drawing that vertical line there is because sometimes in our conversations we'll be interested in talking about an augmented matrix. Sometimes in our conversations we're talking about the coefficient matrix. And without that line there, it's not clear what we're talking about, right? It's not clear whether the matrix I show you is augmented or coefficient matrix. So I really like drawing that line there when we're talking about an augmented matrix, just so that we know that that's what it is. So if we don't see that vertical line, we know it's the coefficient matrix. Anyway, um, the next thing we want to talk about, now we've talked about how to change a system of equations into a matrix. The next thing we want to talk about is how can we take this matrix and make changes to it so that we could solve that system of equations. So we're going to do what are called row operations. There are going to be 3 row operations we're allowed to do to produce an equivalent system. Again, my goal here is make changes to the matrix while still retaining the same solution, right? That's what we mean by equivalent systems. So these are row operations. We're going to make some changes to the rows. So the first row operation we're allowed to do is where the rows are switched. We call that interchange. So basically, if I just take 2 matrices and swap them, we call that an interchange. So please notice in this case, the matrix on the left, if we swap the first and second rows, the result will be the matrix on the right. So what's happening is that row 1 and row 2 are being switched. And by the way, I'm going to use this notation. I encourage you to do the same thing, at least at first, just so you can show what it is you're doing to go from one matrix to another. I'm not going to do this forever, but probably for the first 2 or 3 lessons, I'll do that, just so you can follow my work while we get used to performing these operations. So the first row operation is an interchange. The second operation is where a row is multiplied by a non-zero constant. This is called scaling. Notice in this example, the bottom row changes. This time the bottom row, it looks like every entry in the bottom row is multiplied by 4. So in this case, row 3 turns into 4 times row 3 because each entry in row 3 is multiplied by that 4. By the way, we can multiply by any number, even fractions. I could have taken that matrix and multiplied it, or the bottom row, and multiplied it by 1/2. That's okay, right? Okay, instead of multiplying, maybe you want to say divided by 2, whatever, same thing. The only thing is it can't be all zeros. Or we can't multiply by 0. That's not okay. The third one, and this is the one that we'll probably use most frequently. A row can be replaced by the sum of itself and a multiple of another row, and we call this replacement. So consider this example that we've been working with. First of all, please notice that the row that changed is the bottom row. Right? The bottom row is changed. And what I want to notice is that it looks like the bottom row, oops, sorry about that. It looks like the bottom row is replaced by itself plus row 2, right? Because notice if I took row 2 and row 3, this first column, row 2 plus row 3 is 1, and so I put a 1 in the third row. Row 2 plus row 3 is 3, and that goes in the bottom row. Row 2 plus row 3 is 3, that goes in the bottom row. Row 2 plus row 3 is 3, that goes in the bottom row. So I added the second and third row, and that's what replaced the third row. That's what got put into that third row. Okay, so that's a list of 3 things that we are allowed to do. Those, by the way, those are the only 3 things we're allowed to do. that would result in an equivalent system to the one we started with. Next, we want to talk about some different, very, very useful forms that a matrix can take. Um, and the first one here is called echelon form. And by the way, just so you know, um, if you ever hear me say row echelon form, it's the same thing. It's just a different book that I've used before calls it row echelon form. And so fairly frequently you'll find that I slip and say that, but basically it means the same thing. Echelon form has two characteristics. The first characteristic, a matrix in echelon form, any row that has all zeros will be at the bottom. Okay, so that's the first requirement. The second requirement is any lead entry, which are called, which would be the first, or let me explain what I mean in a second. Any lead entry has zeros below it. Now, here's what I mean by lead entry. For any row, if we were to read it from left to right, the first entry we come to that is not a zero, we're calling that the lead entry. And if that entry has all zeros below it, then we are in echelon form. This is a little confusing. I know that, but I'll show you what I mean in just a second. So each lead entry, meaning the first non-zero number we come to as we read it from left to right, the first non-zero number we come to has zeros below it. So these are the two requirements to be in what's called echelon form. We have another one called reduced echelon form, where now we have two extra conditions. The first condition is that all those lead entries have to be ones. In echelon form, the lead entries can be anything but zero. But in reduced echelon form, the lead entry has to be one. They all do. And those ones have to have zeros not only below, but now they have to have zeros above as well. We call that reduced echelon form. All right, so let's look at some examples. Here's some examples that are in echelon form. So again, the one on the left there are no rows with all zeros, so that doesn't matter. Notice the one on the right, there's a row with all zeros, so it's down here at the bottom. Each row, the first row, here's my non-zero entry, and it's got zeros below it. The next row, as I read from left to right, the first non-zero number I come to, that's my lead entry, and it's got zeros below it. And then the next row, the lead entry, the first non-zero number I come to is here, and there's nothing below it. So that's echelon form. Here our lead entries are this 1 with zeros below. The first non-zero entry is a 3, and there's zeros below there. And then 1, there's zeros below. And the bottom row doesn't have a lead entry because the bottom row is all zeros. Before we go any further, I've been saying lead entry, which is great. It's a little hard to say, but it doesn't matter. I'm going to start referring to those spots, the numbers that I just circled here. I'm going to start referring to those as pivot positions. And I'm going to define that later. And you may even see as we do some work here as we go along, why I call that a pivot position. But I'm just going to start using that phrase because that is really what we're going to be seeing throughout this course. We're going to refer to those as pivot positions. So on the matrix there on the left, each of those pivot positions are 1. But again, in echelon form, that's not required. So the one on the right there, one of the pivot positions is a 3, and that's fine. That's acceptable. Here's a couple more just generalizing. In this case, each of those pivot positions has a little square in that spot. All the stars can be any number at all, doesn't matter. And then below each of these pivot positions, we have to have zeros. And in the lower left matrix there, the bottom 2 rows are zeros. So there are no pivot positions there. And here the first non-zero entry is this box with zeros below. This one with zeros below. You get the point. And then the last row here's the pivot position with nothing below it. Okay, and again, those are boxes because they can be any number. Okay, those are the pivot positions. Now, and by the way, these are also sometimes called triangular form because you can create a little triangle. Sort of kind of looks like a triangle of zeros. Or the top triangle is the triangle of numbers. I don't know, whatever. Triangular form. Okay. Now, for reduced echelon form, now we still talk about pivot positions, but now they have to be all zeros, or all ones, excuse me. And now these pivot positions have to have zeros not only below, but also above. Here's my pivot positions, 1, 1, and 1. Again, in a reduced echelon form, they all have to be 1s, with zeros both below and above. So these are reduced echelon form. Here's some more, just general echelon or reduced echelon forms. Notice we don't have those boxes anymore because now my pivots have to be 1s. So we have all these 1s. So like, for example, here's a 1, zeros both above and below. Notice this column does not have a pivot. So this number can be anything, right? We're back to that star. Here's a pivot. So we got zeros above and below. But this column, there is no pivot. So these numbers can be whatever they want to be. So we got those stars. Okay, so we've talked about what we're allowed to do to change a matrix. We've talked about the forms that we want the matrix to become, echelon form or reduced echelon form. The next thing we have to talk about is how to make that happen, right? How to use our row operations to put a matrix into echelon form or reduced echelon form. And so here's our method. To put a matrix into reduced echelon form, we're going to use either scaling or interchange to place a non-zero number, preferably 1, but it doesn't have to be, in the upper left-hand entry. And then we're going to use it, and I'm going to underline that. We're going to use it with replacement to get zeros below. So we're going to put we're going to basically decide what is our first pivot position, and then we're going to use replacement to get zeros below that pivot. And then we're going to move down and to the right, identify our next pivot position, and use it to get zeros below that. And then down and to the right, find the next pivot, get zeros below. And we're just going to keep going through that process till we get to echelon form. We're going to do lots of examples. If this is confusing, I completely understand. We'll do some examples so you'll see what I mean. Now, if I want to get into reduced echelon form, step 1, echelon form. Okay, so go that far. Then we're going to keep going. Now we're going to start with that 1 in the bottom right corner, and now we're going to go backwards. Now we're going to use that 1 to get zeros above, and then work backwards up and to the left, whereas before we went down and to the right. Again, describing this in words is super confusing. Let's look at an example. Let's solve this system. And by the way, in solving this, we're also going to see why echelon form and reduced echelon form are so incredibly useful. Okay, step 1. I'm going to convert this into my augmented matrix. So I'm going to change this. So the top row, the coefficients are 1, -2, 1. I'm going to draw my little line, and the constant term there is 0. The second row, notice there is no x1, so the x1 column has a 0. We have 2, -8, and then 8. The bottom row, the coefficients are -4, 5, 9, and -9. So there's my augmented matrix. Now I'm going to use row operations. So again, the next thing I want to do is get a pivot in my upper left-hand corner. Now again, 1 is the most useful pivot, but it doesn't have to be 1. It can be anything. It can be anything but 0, I should say. So we've got a 1 in the upper left-hand corner, which means that the first row is exactly what I want. I'm not going to change it. And now I'm going to use that 1 to get zeros below it. Well, notice the second row already has the 0 where I want, so that one also I'm not going to change any. And now we have to figure out, now we have to figure out how to get a 0 here. Now let's remember what we're going to do. Replacement means we can take this row and add it to a multiple of another row. But again, the row that I'm going to use is the one that has that pivot in it. So I'm going to take the bottom row and I'm going to add it to a multiple of the top row. And the multiple that I'm going to pick is going to result in this column turning into a 0. So notice that if I take the top row and multiply it by 4, this 4 added to this -4 is going to give me a 0 exactly where I want it. So what is it I'm doing? Let's denote it here. My row 3 is going to turn into row 3 plus 4 row 1. Or maybe a better way of describing this is the top row times 4 plus the bottom row gives me 0. Now I have to do the same to all the other columns too. So the top row times 4 plus the bottom row, so that'd be negative 8 plus 5 would be negative 3. Top row times 4 plus the bottom row, so 4 plus 9 gives me 13. And then top row times 4 plus the bottom row would be negative 9. Okay, so I've got a pivot in the upper left-hand corner, and now I've created zeros below it. Okay, now once I've got a pivot in this spot, now I'm going to go down and to the right, and now I want to pivot in this spot. Now, as I said, 2 is a fine number to have a pivot. That's okay. But if you can find a convenient way to make that into a 1, that would. So to get a 1 there, we have a couple of options. In this case, I'm going to notice that if I take the second row and just divide it by 2, so I'm going to replace row 2 with half of row 2. So the top row I'm not changing, the bottom row I'm not changing. If I just take the middle row and divide it by 2, I get 0, 1, negative 4, 4. And so now we've got that 1 in that pivot position that we wanted. Awesome. Okay, so we've got the 1 where we want it. Now, again, we're going to use it to get zeros below. And again, the top row, we're not changing any. It's exactly what we want. The second row, we've got that 1 in pivot position where we want it. So now it's just the bottom row. We want to, again, we want to use this 1 to make this turn into a 0. So notice if I take this 1 and I multiply it by 3, adding to this row is going to cancel. So I'm going to take row 3 and replace it with 3 times row 2 plus row 3. Now, I'm going to caution you here a little bit. Make sure you do this for every column, right? So 3 times the second row plus the bottom row, it's 0. But the reason I say that is we did some work to make sure that there were zeros under that first one. We want to make sure that the work from here on out doesn't mess that up. So we still want to double check. Multiply by 3 plus the bottom row, yep, still 0. Good. Multiply by 3 plus the bottom row is 0. Come on. Come on. Multiply by 3, and then plus the bottom row gives me a 1. And then the last column, multiply by 3 is 12, plus the bottom row is 3. Okay. Now, I want to point out that at this point, our matrix is in echelon form. We've got, first of all, none of the rows are zeros, so that doesn't matter. We've got 1s in the pivot positions and zeros below them all. This is echelon form. Now, in a second, we're going to continue into reduced echelon form, but I want to show you that echelon form actually is not a bad place to stop anyway. I'm going to take this now and I'm going to put it back in terms of my x1, x2, x3. So the top row says x1 minus 2x2 plus x3 equals 0. And then we have x2 minus 4x3 equals 4. And the bottom row says x3 equals 3. Remember my goal. My goal here is find x1, find x2, find x3. Oh, here's my x3. And notice it's kind of nice. Hey, once I know x3, I can plug that in here. x2 minus, let me see if I can fit it in here. x2 minus 12 equals 4. So it looks like x2 is equal to 16. And then if I plug those into the top equation, I get x1 minus 6 plus 16. Nope, I did that wrong. Sorry. The point is, The point is, when it's an echelon form, this becomes a very simple equation to solve. Because I just have to take my x1, my x2, and my x3 and plug them in here. So if I plug that in, we get x1 minus 32 plus 3 is equal to 0. So x1 is equal to 29. So unlike the matrix we started with, by being in echelon form, it becomes a matter of just take one answer, plug it back in to find another answer, plug it back in to find the last answer, which is awesome. Okay, now let's see what happens if we keep going to reduced echelon form. Now let's remember how to do that. I'm going to take my echelon form matrix. Now I've got a 1 in this pivot. I'm going to use it to get zeros above. Going to reduced echelon form, now we're going to work backwards. Now the bottom row is good. And now I'm going to use it to get zeros above. So notice if I want to turn this into a 0, I basically need to take the top row and subtract the bottom row. So my row 1 becomes row 1 minus row 3. Again, do this for every column. Okay, so we've got row 1 minus row 3 is 1. Row 1 minus row 3 is -2. Row 1 minus row 3 is 0. Row 1 minus row 3 is -3. Okay. I need to use this 1 again to cancel with this 4. So it looks like I need to multiply the bottom row by 4 and then add it to the second row. So row 2, so I'm going to do 4 times row 3 plus row 2. So again, multiply the bottom row by 4 and add the second row, 0. Multiply the bottom row by 4, add the second row is 1. Multiply the bottom row by 4, add the second row is 0. Multiply the bottom row by 4 is 12, plus the second row is 16. Okay, and then we're almost done. We've got, come on, we've got our pivot here, and now we've created zeros above it. So now let's move on to this pivot here and get zeros above there. Here's my pivot. All I've got left is get a 0 above it. So notice that my row 1, I need to take the 2 times the second row and add the first row. So again, second row is fine. Third row is fine. If I take 2 times the second row plus the first row is 1. 2 times second row plus the first row is 0. 2 times second row plus the first row is 0. 2 times the second row is 32. Plus the first row is 29. Okay, this now is reduced echelon form because now we have 1s in the pivots and 0s both above and below. And notice reduced echelon form is even easier to finish because if I put this back into x's, y's, or to x1, x2, and x3, the top row says x1 is equal to 29. Second row says x2 is equal to 16. The third row says x3 is equal to 3. Same answer we got the other way, but notice that now all the work was in the matrix. We didn't even have to take the numbers and plug them in. Just all we had to do really is put it into reduced echelon form, and then we could read the answer right off the matrix, which is kind of cool. Um, on tests and things, the directions will just say solve the system. I'm not going to I'm not going to tell you it has to be reduced echelon form or it has to be echelon form. I'm not going to ask you that. So the choice is yours. If you like the idea of stopping here and then put the x's back in and solve it. By the way, on the next slide I'm going to tell you this is called back solving. Um, Basically taking the x3 and back solving to find x2 and then back solving to find x1. So if you like that method, great. If you want to keep going to put it into reduced echelon form, that's also perfectly acceptable. Now, I might say put this matrix into reduced echelon form, but when it comes to solving a system of equations, I'm not going to dictate one method versus the other. Okay, I want to point out in this case, in this system, we got one solution. And so because there was a solution, we call that consistent, as I said before. Okay. Um, a matrix and echelon form may be different depending on the row operations you choose. As we went through and do it and did this problem, we made certain choices, and we could have made different choices. I, I would say that I made the choices to make this as easy as possible, but there's certainly other choices we could have made. We would have ended up getting a different echelon form matrix. It wouldn't change our answer any, but the echelon form might have looked differently depending on the different choices we made. Echelon form matrices are not unique. Reduced echelon form matrices are. No matter what choices I made, if I kept going to the reduced echelon form, they're all going to look like this. Okay. And as I said before, another option is to stop at echelon form and then backsolve. We talked about that. Okay. Before we go any further, we're going to do some more examples, but I want to tell you this process of putting a matrix and doing row operations and putting it into echelon form or reduced echelon form, this is something we are going to be doing a lot. I can't think of a single lesson in this whole course where we don't use row operations, where we don't put a matrix into echelon form. It comes up a lot. So it is definitely worth the time to put in now. Understand this process. Know how to put a matrix into echelon form and reduce echelon form because it will definitely be worth the effort. All right, let's do this example next. As I said, step one, let's put this into an augmented matrix. So we get, let's see, I'm going to, I just put the numbers in here. So we get 0, 4, 0, 1, negative 4, 8, 2, negative 3, 2, 1, and 5, negative 8, 7, 1. Okay. Next thing we want to do is put a non-zero number in the upper left-hand corner. And it really doesn't matter. In this case, I don't think there's an easy way. One is preferable, certainly. I don't think there's an easy way to get a one in the upper left-hand corner. That's fine. I'm just going to switch the first and second rows. So row one and row two, I'm just going to swap. And so we get 2, negative 3, 2, 1. This becomes 0, 1, negative 4, 8. And the bottom row is staying the same. Okay. Next thing is we've got a 2 in this pivot position. I want to get zeros below it. And so that means that the first row is fine. Second row is fine because we've already got that 0 where we want it. The third row. So here's what we're going to do for the third row. And this is going to be a little bit different, maybe a little bit different. I'm going to multiply the top row by 5. I'm going to multiply the bottom row by negative 2. It's a little differently than we've done. And we've really only multiplied one row by a number, but we can multiply 2 by a number and it'll work out. So 5 times the top row, negative 2 times the bottom row, and then add them together. 5 times the top row, negative 2 times the bottom row gives this a 1. 5 times the top row is 10. Negative 2 times the bottom row is negative 14, so that's negative 4. 5 times the top row is 5. Negative 2 times the bottom row is negative 2, so this becomes 3. Okay, so we've got a 2 in that pivot position, zeros below it. Now I have my new pivot position. We want to get zeros below there. And so it looks like I can just take row 3 and replace it with row 2 minus row 3. So we got 2, negative 3, 2, 1, 0, 1, negative 4, 8, 0, 0. Negative 4 minus negative 4 is 0, and 8 minus 3 is 5. Okay, this is now in echelon form, but also this is going to be a problem. And here's why this is a problem. If I were to put x's back into this problem, into this problem here, Notice that the bottom row is going to tell me 0x1 plus 0x2 plus 0x3 is equal to 5. Basically, the bottom row is telling me 0 equals 5. Well, that's not good because basically that is a false statement. And so, because we ended up with a false statement, we're going to say that there's no solution. If all the variables disappear and what you're left with is a false statement, then we're going to say that there is no solution. And in fact, we're going to say that this system is inconsistent. And I used that phrase earlier, inconsistent. What I want to make sure we understand though is this was not, we did, the no solution here wasn't because the variables disappeared. It's because we were left with a false statement. What if something different had happened? What if instead of a 5, what if this had also ended up being a 0? Notice now the bottom row says 0 equals 0. That's a true statement, right? So no solution means we get something that is blatantly false, right? We're, again, inconsistent. It doesn't make sense. If we get 0 or equals 0 on the bottom, that's fine. There could still be a solution. So anyway, just important to notice that just because all the x's disappear doesn't mean it's automatically no solution. So be careful about that. All right, next up, and this I've already kind of talked about this. So it's a pivot position in a matrix X is a location in A that corresponds to a leading one in the reduced echelon form of A. Again, the way that we've been defining pivot positions before. A pivot column is a column of A that contains a pivot position. So in this example, go back here. In this example, the pivot columns were columns 1, 2, and 3. And by the way, the pivot columns in the reduced echelon form are also the pivot columns of every other iteration of this matrix. So once we've identified at the very end what the pivot columns are, then that is true throughout the rest of the problem. And by the way, we can identify them just from the echelon form, right? As soon as we know where our pivot positions are, we know our pivot columns. Notice in this example, our pivot columns are column 1, column 2, and column 4. And in this case, we ended up getting no solution. So the observation here is that in the previous system, it was inconsistent because the rightmost column was a pivot column, right? In this case, because there was that 5 in the rightmost position on the bottom row, we ended up getting a false statement. Consider that version that was blue there, the alteration there. What about if I had that matrix? It was 2, -3, 2, 1, 0, 1, -4, 8, 0, 0, 0. And again, let's say that last entry was also a 0. Notice now our pivots are just the 2 and the 1. The bottom row is all zeros, so there is no pivot position in that bottom row. So notice in this blue matrix, now it's only the first and second column that are pivot columns. And so now the pivot column was not the rightmost column, and so we did not get an inconsistent result. We will actually get a solution to that blue matrix if we were to continue. So again, that pivot column being the rightmost column is the reason we got an inconsistent system. Okay, so let's play around with this matrix. Let's put this matrix into echelon form. Sorry, reduce the matrix to echelon form and then locate the pivot columns. Notice again, it's really all we need to worry about is the echelon form. Because as soon as it's an echelon form, we've identified what the pivots are. By the way, please notice, I didn't say this was a augmented matrix or a coefficient matrix. I didn't say anything. This is just an arbitrary random matrix that we're going to put into echelon form. And there will be no conversation in this case about whether it's consistent or inconsistent, if there's a solution, that conversation doesn't even make sense because we don't know how or even if this matrix is linked to a system of equations. This might just be a random matrix that isn't linked to anything, and that's fine. That's completely okay. Okay, let's put this in echelon form. So I want a 1 in the upper left-hand corner. I'm going to switch the top and bottom rows. So let me just get back to black here. Okay, so I'm going to switch the top and bottom rows. So row 1 and row 4 are going to switch. So the top row is now 1, 4, 5, -9, -7. Second row doesn't change any. Third row doesn't change any. And the bottom row becomes 0, -3, -6, 4, -9. So we're going to put this into echelon form so that we can identify the pivot columns. Okay, row 1 is good. Row 2, I'm going to replace with row 1 plus row 2. Right, we've got that 1 in pivot position. Let's use it to get zeros below. So row 1 plus row 2, row 1 plus row 2, row 1 plus row 2, row 1 plus row 2 is -6, row 1 plus row 2 is -6. I'm going to write in the bottom row because that also is not going to change. We got the 0 where we want it. For the second row, or I'm sorry, the third row, notice if I take the top row times 2 and add the third row, that'll give me what I want. So the top row times 2 plus the third row is 0. Top row times 2 plus the third row is 5. Top row times 2 would be 10, plus the third row is still 10. Top row times 2 is -18, plus the third row is -15. Top row times 2 is -14, plus the third row is -15. Okay, so I've got a 1 in my pivot position. Okay, and we got zeros below it, which is great. Now I want a 1. I'm going to move down 1 and over 1. Now I want a 1 here. And again, it doesn't have to be 1, but if I can find a convenient way to put a 1 here, that'll make my life a little bit easier. Notice that middle row, I can divide it by 2, and it'll do what I want. So row 2 is going to be replaced with 1/2 of row 2. So that'd be 0, 1, 2, -3, -3. While I'm at it, and you absolutely do not have to do this, but I'm also going to notice that the third row, I can easily divide that by 5 without creating fractions, which there's nothing wrong with fractions, but if I can avoid it, I'm going to. So I'll divide that by 5. We get 0, 1, 2, -3, -3. Now, the bottom row, listen, you could divide the bottom row by 3. Notice it would create a fraction, which is annoying, and so I'm not going to, but there's nothing wrong with fractions if you want to work with them. So we get 0, -3, -6, 4, -9. Okay, so now we have a 1 in this pivot, and so now we want to get zeros below that. So row 1 is fine the way it is. Row 2 is fine the way it is. For row 3, I'm just going to do row 3 minus row 2. So we get 0, 0, 0, 0, 0, fairly boring. For row 4, I'm going to multiply 3 times row 2 and then add that to row 4. Because again, I'm using this 1. Notice if I multiply it by 3 and then add the bottom, they're going to cancel out. So the second row times 3 plus the bottom row is 0. Second row times 3 plus the bottom row is 0. And another 0. And then -5. And then by 3 and then add. Well, I just want to make sure I didn't mess something up. Yeah, that's fine. Multiply by 3 and then add gives me -18. Okay, and then finally, whoops, and then finally to put this into echelon form, I'm going to swap the second and third row, or the third and fourth rows, I mean, because notice that we need all the zeros on the bottom. If there's a row with all zeros, it goes on the bottom. So we got 1, 4, 5, -9, -7, 0, 1, 2, -3, -3, 0, 0, 0, -5, -18, and 0, 0, 0, 0, 0. There's my echelon form. My pivots, my pivot positions are this one, and this -5. So my pivot columns are column 1, column 2, and column 4. Okay, there we have it. So there's my pivot columns. And again, if nothing else, this example gives us a chance to practice row reduction some more. Okay, let's consider this system where this is our augmented matrix, and sorry, the augmented matrix has been changed into this reduced echelon form. So basically, saving us all the work. Here's our reduced echelon, right? We got pivots in these two positions, zeros above and below. Notice that in this case, if we put x's back into the problem, we get x1, x2, x3 there. Notice we're going to say that x1 and x2 are basic variables, and we're going to say that x3 is a free variable because it's free to be anything. Here's what I mean by that. Notice that x1 can be written as 1 plus 5x3. x2 can be written as 4 plus x3. And then x3 is, again, I'm going to write the word free there because it can be whatever it wants to be. Notice that this is going to be a situation where there are many solutions. There are lots of solutions here. And we can actually describe all of those solutions. We can describe them where basically you can pick any number for, again, there's many solutions. Pick a number for x3, and then these equations will tell you what to pick for x1 and x2. So for example, if you pick, I don't know, 2 for x3, we know that x1 is going to be 1 plus 5 times 2 is 11. x2 is going to be 4 minus 2, which is 2. So one of the solutions is 11, 2, 2. You could pick 0, right? I'll pick 0 for x3. If x3 is 0, x1 is going to be 1 plus 5 times 0. x2 is going to be 4 minus 0. So another solution is 1, 4, 0. The point here is there are many solutions. We can describe those many solutions with these equations. And the many solutions, each of those solutions comes from picking a different value of my free variable, which in this case was x3. Let's take a look at this example. Now, this example is already in echelon form. And we want to find the general solution. Again, general solution just means describe them all. Okay. We've got this in echelon form, but to finish this problem, to describe all the solutions, we really want reduced echelon form. So we've got our pivots. Let's start with the bottom pivot, and let's use it to get zeros above. So again, echelon form is great, but what we really want is reduced echelon. So we get 0, 0, 0, 0, 1, 7. Oh, and I'm sorry, I must apologize. This is an augmented matrix, says so in the problem. So we are now assuming that this is associated with a system of equations. In fact, let me go back here for a second. This is an augmented matrix, so I'm going to put that line there as well. This example, we weren't told it's augmented, so we don't really, and we don't even care if it's augmented, so we didn't bother with that line. But this is augmented, and so is this one. Okay, so we got the 1 in the bottom row. We want to get zeros above it. So notice that row 2 is going to become row 2 plus row 3. Again, do this with every column just to make sure things don't get messed up. So row 2 plus row 3 is 0. Row 2 plus row 3 is 0. Row 2 plus row 3 is 2, and so on. Right? Don't just assume that the rest of it doesn't change. Double check. So row 2 plus row 3 is 0. Row 2 plus row 3 is 10. Okay. We want to get the top row. We also want to have a 0 above that pivot. So now my row 1, I'm going to do 2 times row 3 plus row 1. And we're going to get this. So multiply the bottom row by 2 and add the top row, makes this a 0. Multiply the bottom row by 2 is 14, plus the top row is 10. Great. So we've got a 1 in the lower right-hand corner with zeros above it. Let's move to the next pivot. Now remember, in echelon form, this number can be anything, but in reduced echelon form, that needs to be a 1. So the next thing I'm going to do is take my second row and just multiply by 1/2. And by the way, that is always the most direct way to get a 1 in that pivot position. It might result in fractions. Fortunately, it doesn't this time. But just notice that if you've got a number in that pivot that is not a 1, but you want it to become a 1, just multiply that or just divide that row by whatever's sitting there. And then automatically you're going to get a 1 in that pivot position. So just a little trick there. So the middle row I'm dividing by 2. Top row doesn't change any. Okay, now we've got a 1 in pivot position. And so now, again, second row is fine. Bottom row is fine. And so now it's just the top row. So the top row, I'm going to do -2 times the second row plus the top row. Oops, should be 6. So 1, 6, 0. So it's the second row times -2 plus the top row. This is a 3. Second row times -2 plus the top row gives me a 0 here. Okay, so now what happens if I now put this back into x's and y's? Because now I'm in reduced echelon form. Now I can put x's and y's back. So let's remember, before we go any further, let's remember that this was the x1 column, x2 column, x3 column, x4 column, x5 column. You don't have to write that, but it's just useful to remember. So the top row says x1 plus 6x2 plus 3x4 is equal to 0. The second row tells me that x3 minus 4x4 is equal to 5. And the bottom row says x5 is equal to 7. Now, when I describe my solutions here, I basically, any problem, I'm asking the question, what is x1? What is x2? What is x3? What is x4? And what is x5? That's really my big question. Well, the top row tells me that x1 is equal to -6x2 minus 3x4. The second equation tells me x3 is equal to 4x4 plus 5. And the bottom row tells me that x5 is 7. What that leaves me with is x2 can be anything. I'll call that so that's my free variable. x4 can be anything. So I'm going to call that my free variable. And notice that x2 and x4 are free. All the rest of them are described in terms of those two variables. In fact, another way I could express this I could even give names to those two variables. x2, I could call that, I don't know, t, and x4, I could call that u. So notice that x1, now I could write that as -6t minus 3u. x3 would be 4u plus 5. And, well, x5 is just 7. It's fixed. But the point is I could do that also if I wanted to. I could write it where instead of writing x, listen, there's nothing wrong with leaving it as x2 and x4. It's just a little bit easier to write it as t's and u's. And in fact, when we write in that position, in that form, we call that the parametric vector, or let's try again. We call that the parametric description of the solution set, where those letters t and u are what we call parameters. Um, the free variables could be considered to be parameters. And so again, instead of t and u, you could just say x2 and x4. Those are also parameters. That's fine. Um, Now let's think about that matrix for a second. Notice that the basic variables corresponded to the pivot positions. Think about it for a second. If this was my x1 column, x2, x3, x4, x5, from the very beginning, I recognized that my pivot columns were column 1, 3, and 5 because there's where my pivot positions are. Well, notice that my pivot columns, those variables, were my basic variables. So x1, x3, x5, those were my basic variables. And my free variables came from columns that had no pivot. So so we don't even need the reduced echelon form. The echelon form, we can identify which are the pivot columns and which are not. And then that'll tell us right away which are my free variables and which are my basic variables. You still need the reduced echelon form to describe those, but at least we can identify them just from the echelon form. So if a system is consistent, then the solution set either contains a unique solution, and of course, unique solution means that there are no free variables. Each variable has only one answer. There's no parameters or anything. So consistent means either there's one solution, so no free variables, or there's infinitely many solutions, meaning that there's at least one free variable. Maybe there's one, maybe there's two, like the last example, maybe there's more than that, who knows? But infinitely many solutions means there's at least one free variable, at least one parameter. Okay, that brings us to the end of the lesson. Thank you very much for listening and watching.